Good day everyone, my name is Mykyta and today I am going to present our work titled Dynamic Feature Weighting in Hybrid Recommendation Systems using Genetic Algorithm, which focuses on improving hybrid recommendation systems through adaptive feature importance optimization. As the volume of digital content grows, recommender systems have become essential for helping users find relevant information. The two most common approaches, collaborative filtering and content-based filtering, each have well-known strengths and limitations. To combine their advantages, researchers often turn to hybrid models. However, these models frequently rely on fixed feature importance, assuming all user and item attributes contribute equally to recommendation quality. This assumption is rarely valid in practice. In our previous work, we explored the categorization and robustness of features in hybrid systems. Building on that foundation, this study addresses a natural next question. Can we automatically learn the optimal importance of each feature rather than assigning weights manually? The goal of our study is threefold: to develop a hybrid recommendation model that dynamically adjusts feature weights, to apply a genetic algorithm for discovering optimal weight distributions, to evaluate the impact of dynamic weighting on recommendation accuracy. We aim to improve personalization while reducing reliance on expert design feature engineering. Our proposed system follows a modular hybrid architecture. It integrates predictions from both collaborative and content-based components. It represents users and items via feature vectors, including demographic data, content genres, and interaction history. A weighting mechanism governs the influence of each feature. What distinguishes our approach is that these weights are not fixed. Instead, they are learned dynamically through evolutionary optimization. Why use a genetic algorithm? In our earlier hybrid recommendation approach, we treated all features equally when calculating similarity between users. These features included demographic attributes such as age, gender, profession, and general interest indicators. Each was assigned an equal weight. However, in real-world usage, this assumption fails. Different users care more about some features than others. For example, one user may prioritize gender preferences, while another may value age proximity. This discrepancy limits the system's ability to personalize recommendations effectively. To overcome this limitation, we propose using a genetic algorithm to dynamically learn the most suitable weights for each feature based on actual user behavior and preferences. Traditional feature weighting methods rely on manual tuning, which is time-consuming and inconsistent, domain knowledge, which may not generalize across datasets, and static values, which don't adapt over time. Genetic algorithms provide an alternative by offering a heuristic optimization method inspired by natural evolution, robust handling of non-differentiable multimodal search spaces, a way to automatically discover feature importance patterns that improve recommendation accuracy. This makes genetic algorithm well suited for adaptive optimization of feature weights in recommender systems. A genetic algorithm is an evolutionary search process that evolves a population of solutions over time. Key concepts include population, a set of candidate solutions called chromosomes, chromosome, a vector of representing a particular combination of feature weights, gen, a single element in a chromosome, for example, it's just one feature weight, and allele, the specific numeric value assigned to a gen. These components work together to explore the solution space efficiently, seeking combinations that yield better recommendations. The genetic algorithm operates through iterative evolution. Each generation includes the following steps. Population initialization, randomly generate feature weight vectors to form the first population. Fitness evaluation, calculate how good each chromosome and how well its weight combination predicts user preferences. Selection, choose the best performing chromosomes based on fitness. Crossover, combine pairs of chromosomes to produce new solutions. Mutation, introduce small random changes to ensure diversity and avoid local minima. Survival selection, retain the best chromosomes for the next generation. And termination, stop when improvement stalls or after a fixed number of generations. This process allows the genetic algorithm to converge toward an optimal or near optimal set of feature weights. Defining the fitness function. The fitness function is central to guiding the evolution. It tells us how well a particular set of feature weights predicts actual user ratings. The fitness function evaluates each chromosome's effectiveness by measuring the accuracy with which it predicts user ratings. This accuracy is quantified using mean absolute error, which lower values indicate higher fitness. A chromosome with lower error values effectively uh, indicates that its corresponding weights allow for more accurate predictions of user preferences, so enhancing the overall recommendation quality. Once optimized weights are found, we integrate them into a fuzzy distance function used to calculate user similarity. The adaptive weighting approach leverages the genetic algorithm to dynamically optimize the relative importance of each feature, so its weight. The global fuzzy distance function, originally introduced in our previous work, is adjusted using these adaptive weights to more accurately quantify similarity between users. By allowing the algorithm to set certain weights to zero, irrelevant features can effectively be disregarded, ensuring that the recommendation system continually adapts to user preferences, and thus significantly improves recommendation accuracy and personalization. Experiments and results. In this experiment, we evaluated the impact of adaptive feature weighting applied only to general interest indicators or GIIs on the performance of a hybrid recommender system. Our baseline configuration is a hybrid model which was used with static uniform weights for all features, including demographic attributes and GIIs. And the user similarity was calculated using a global fuzzy distance function with equal contribution from each feature. And our adaptive configuration, which is being proposed, we employed a genetic algorithm to learn optimal weights for GIIs, keeping demographic features unweighted. Each chromosome represented a vector of weights assigned to individual genders. The genetic algorithm iteratively evolved the population of weight vectors over several generations. The fitness function was defined as the inverse of mean absolute error between actual and predicted ratings. At each generation, similarity between users was recalculated using the updated weighted fuzzy distance function. And on the left, figure shows how the fitness of candidate solutions improved steadily across generations. This indicates that the genetic algorithm was successfully learning better feature weight configurations over time. Figure on the right visualizes this evolution. We see a smooth and consistent upward trend in fitness scores. It reflects how the model became increasingly effective at capturing user interests. An interesting observation comes from the final set of learned weights. Genres like adventure, musical, and romance were given more importance, suggesting they had a stronger influence on recommendation quality. In contrast, genres like drama or documentary were weighted lower, implying less impact for this dataset. These results not only confirm that adaptive weighting enhances accuracy, but also show the model's ability to learn domain-specific insights, all without manual tuning. Overall, the approach proved based, practical, and reliable, leading to more personalized and robust recommendations. In conclusion, this work presented a hybrid recommender system enhanced by adaptive feature weighting through a genetic algorithm. By learning optimal feature weights, the system moves beyond static, uniform assumptions, dynamically adjusting to user preferences. Our approach improved recommendation accuracy and increased user coverage, offering both theoretical validation and practical benefit. Visualization of the genetic algorithm's evolution confirmed stabilization and highlighted which features are most influential in prediction. The system automatically identifies which user preferences matter most, enabling more accurate and diverse recommendations without manual tuning. This adaptability is especially useful in areas where the user interests change quickly or where the content is very diverse. That's all. Thank you for your attention.